I did not take note where we stopped, but I guess I assigned you the task of the ISO OC7 layer model where you had to map these tasks to layers in the ISO OC layer. And slide-wise, I guess we stopped at reference models. So if this is not correct, then please let me know such that I can start from the correct spot where we left off. But anyhow, I guess we should talk about the mapping of the ISO OC 7 layer model. Excuse me? Can you say it again, please? Or maybe this was unrelated. Okay, so here in this task, we have 15 phrases, and we need to map these phrases to the 7-layer model of the ISO OC. So let's go through these. Put an electrical signal onto the transmission medium. This is clearly the physical layer because this is one of the main tasks of the physical layer. Splitting a message into packets. Here, two answers are possible because it depends on the direction in which you pass the 7 layers of the ISO OC model. So if you do top down, so you are on the sender side and you pass the layers starting from the application layer and finishing in the physical layer, then the packaging mechanism is done in the transport layer where we do segmentation and reassembly. But if you're on the receiver side and you pass the layers from bottom to the top, then the bit stream that comes in from the physical layer is framed, which is also a packaging mechanism that happens in the data link layer. Then next, establish and terminate the communication session. Well, as I mean, the solution is right in the phrase, it's the session layer. Request an HTML file from a web server. This is one of the main tasks of the HTTP protocol. So this is something related to an application protocol that uses the transport layer in order to do network communication. This would be application layer. Then 5, identify the target application of a packet. These are port numbers, and port numbers are defined in the transport layer. 6, reorder a set of packets. This is the reassembly step in the transport layer. 7, identify the physical address of a host. Physical addressing happens at the data link layer. Logical addressing happens at the network layer. So this is the difference between a MAC address and an IP address. And then 9, convert a message into units consistent with the transmission medium. This is a tricky one. Because converting a message into units consistent with a transmission medium, meaning that you prepare the message to fit to what the physical layer is capable to do. And this happens in the data link layer. And this is the reason why most of the protocols that are for the physical and the data link layer span over these two layers. So the two most prominent ones being Ethernet, or we have 3 prominent there: Ethernet, Wi-Fi, and Bluetooth. If you take these 3 like protocols, and if you read the documents, the standardization gremium wrote the documents to cover both the data link layer and the physical layer, because these 2 layers are very close and tied together, because the data link layer needs to know how big a Ethernet frame, for example, needs to be constructed in order to be modulated in an Ethernet card. So the hardware supports some certain limits, and these limits need to be respected in the data link layer. So 9 would be the data link layer. Then encrypt a message. Well, here in the exam situation, I would accept 2 answers. You can do, or 3 even so. You can do encryption in the application layer. So encryption can be part of your application layer protocol. Then encryption fits into the presentation layer, because this is one of the purposes that we defined before. And then encryption can happen at the network layer as well. So there is a encryption method / technology that is called IPsec. The VPN of the university, by the way, is based on that technology, IPsec, and IPsec operates at the network layer. So encrypting can happen at the network layer, it can happen at the data, not the data link layer, network layer, presentation layer, and application layer, these three: application, presentation, network. Then handle transmission errors. Well, this can be done basically on any layer. So the data link layer has error control, the transport layer has it, the network layer has it, the application layer can implement it. So basically, any layer can handle transmission errors. Well, handle transmission errors is different from detecting errors. So detecting errors is basically done on every layer, but like handling the layers to like give feedback to the sender that the packet was compromised or lost. This is in practice done at the transport layer. So TCP, being the prominent protocol there, actually handles transmission errors. Detecting transmission errors happens at other layers as well. Then selecting the next hop of a packet on the way to destination. It's a classical routing problem. It's done in the network layer. 13, convert a message into a sequence of bits ready to be transferred. Also tricky ones. So 9 and 13 are a little bit trickier. A sequence of bits ready to be transferred. It can happen in the physical layer, it can happen in the data link layer. So the data link layer like finishes the message, finishes the bit stream, but the physical layer in practice can do modifications to fit the physical characteristics of the transmission medium. So for example, not modulating a square wave, but doing like a sine wave instead. These kind of physical things happen at the physical layer. So in an XM situation, I would accept here both physical and data link layer. Then ensure that a slow receiver is not overwhelmed by a fast sender. This is flow control. Flow control is realized in the data link layer and in the transport layer. And finally, we have protocol multiplexing. Protocol multiplexing is what happens at this slide here. So if you take a closer look at the bottom 3 layers, so the physical, the data link, and the network layer, here you see the examples. So the physical layer and the data link layer, the protocols that are defined for these 2 layers span over these 2 layers. 805.15 is Bluetooth, 802.15 is Bluetooth, 802.11 is Wi-Fi, then 802.3, and then a number is Ethernet. More recent numbers starting from 1997 are called Ethernet 2, and from Ethernet 2 things are special. Because the data link layer, in the data link layer, a lot of things happen. So people decided to subdivide the data link layer into sublayers, the LLC sublayer and the MAC sublayer. What we talked about mostly happens in the MAC sublayer. So physical addressing, error control, flow control, framing. This happens in the MAC sublayer, but there's also an important job that has to be done in the data link layer, which is covered by the LLC sublayer, LLC standing for logic link control, whereas MAC stands for media access control. So this LLC sublayer does protocol multiplexing, because we have a variety of protocols in the network layer. Examples, we have the IPv4 protocol in the network layer. We have the IPv6 protocol, we have the ICMP protocol, and we have the ARP protocol as examples in the network layer. And all these protocols may use the same physical layer, like the same Ethernet card or the same Wi-Fi card that is built into your machine. And in order to do multiplexing, like the same approach as we do packet multiplexing, we can do this with protocols as well. This is the job of the LLC sublayer. And Ethernet 2, so from 1997, defines how this LLC sublayer needs to be structured. Wi-Fi, for example, resorts to a standard that's called 802.2. Bluetooth resorts to an implementation or the structure of the LLC sublayer to a protocol that's called L2CAP. And protocol multiplexing means if you have multiple protocols at the network layer, you decide which protocol is allowed to use the data link and the physical layer, because there can only be one instance per network card. So if you have one network card, then only one packet can be processed at a time at this network card. So we need some kind of protocol multiplexing, and this happens in the data link layer, to be more precise, in the LLC sublayer. Okay, any questions on these? Any questions on this question? No. Then let's go forward and finish the internet reference model. I actually don't know if we talked about the internet reference model. If not, it's not a big deal, because the internet reference model is basically the ISO-OSI model, so the 7 layers, in a more practical perspective. So the ISO-OSI 7-layer model, we know that the data link layer and the physical layer need to be tied together. So the data link layer needs to know which physical layer is in implementation, and the other way around. So these bottom two are close together, and the internet reference model says, well, we merge these two layers into the host to network layer in order to reflect that tied interconnection between data link and physical. And the same happens at the top 3 layers. So the application, presentation, and session layer are merged together into one application layer, because it turned out in practice that the presentation layer and the session layer is not implemented at all. So in fact, a presentation layer and a session layer in practice does not exist. So every task like encryption, decryption, or taking care about a session, a context, this is either done in the transport layer or in the application layer. So the application layer takes over the job of the presentation and the session layer. So the internet reference model taking this into consideration and merges the top to the top 3 layers into the application layer. Then transport and network, in terms of purpose and technologies and protocols, stay the same. The only difference is that the network layer is renamed to the internet layer to promote the name internet reference model, and also not to be confused with the host to network layer, because in the top layer in the internet reference model, there is already the word network in it. So if you have a host to network layer and a network layer, this would be confusing for some people. So the standardization gremium decided to rename the network layer into the internet layer. And that's it. So if I ask you in a exam, compare the ISO-OSI 7-layer model with the internet reference model, then you say, well, the host to network layer is the bottom 2 layers. The internet layer is renamed from the network layer. The transport layer stays the same. And the application layer is a merge of the top 3 layers of the ISO-OSI 7-layer model. So we reduce the number of layers from 7 to 4, and we merge the top 3, the bottom 2, and rename the network layer. In terms of prominent protocols, I can also ask you, give an example for a protocol in each of these layers. Then host to network would be Ethernet, Wi-Fi, Bluetooth, point-to-point. Point-to-point being the protocol that you use in your DSL connection. So if you have a DSL contract with an internet service provider, the router that you have at home and the first network control device of the internet service provider, typically the protocol over a DSL connection is PPP. It's short for point-to-point protocol. Then internet layer or network layer, we have the IP protocol as the most prominent protocol. In transport, it's the TCP protocol. And in the application layer, we have a lot of protocols that are used on a day-to-day basis. So right now I'm using HTTP because I have a browser open. I use DNS to resolve names. I use DHCP, which is a protocol to obtain IP addresses. Oh, in the next one, there's an actual typo. The protocol is called SMTP. So the P and T is flipped. This is the protocol that structures email exchange. FTP is for file transfer. NTP is for time propagation. SSH for remote logins, and so on and so forth. So a lot of services exist in the application layer that uses the transport layer as a like transport service, like a virtual connection from one process to another. Here you see here you see two things. You see the protocols again, and you see a lot of more protocols. But what you also see is the hourglass shape of the protocol stack. So a lot of things are happening. A lot of things are happening in the application layer, and a decent amount of things is happening at the data link/physical layer, so at the host to network layer. And in between, like the IP protocol and ICMP and ARP define the internet/network layer, and in the transport layer we have TCP and UDP. So we have fewer protocols in the middle layers. So this forms like this hourglass shape, and this is also the reason why the Internet Reference Model is also referred as to the TCP/IP reference model, because TCP and IP are typically used in these kind of connections. So if you did not specify it otherwise, the likelihood of you communicating over a TCP/IP stack is very high. Okay, so let's sum this up. What competencies should you have acquired after this chapter now? So you should be able to define all introduce technical terms. You should know what a protocol is. You should know what a layer model is. You should assess protocols in terms of connection orientation and reliability. Is it connection oriented? Is it reliable? Yes or no? You should be able to describe the communication patterns that we discussed last week. So if you remember, this was one way, publish, subscribe, and request response. Then we discussed service models with the client service and peer-to-peer model. You should be able to explain the difference between these models and bring examples. Then we talked intensively about circuit switching and packet switching, discussed benefits and drawbacks. Also, you should be able, well, this is rather explicit, but you should be able to calculate the waiting times for app down or for different scenarios, such as app download or video on demand, and compare the switching methods with it. Then we talked about the ISO OC7 layer model. You should be able to recite the layers in different orders. You should be able to describe the purpose of each layer. You should assign phrases or terms to layers in the model. Compare the models with each other, so the TCP/IP/Internet Reference Model and the ISO OC7 layer model. And you should be able to provide example protocols for the layer. Are there any questions? No. Then let me open up our next big chapter. Which would be open. My presenter crashed again. It's not the most stable software in existence. Okay, now we are good to go. So our next big chapter is network protocols. This would be not the last one, but the one before. So we are close to the end. We do an end sprint after the Christmas break, and then hopefully everyone is prepared for the exam. So network protocols. What we do in network protocols is we primarily discuss two layers. So we discuss 4 layers of the ISO-OSI model. We discuss the data link, the network, the transport, and the application layer. But we won't go into details in the data link layer, and we won't go into details in the application layer. So we focus on the core of networking protocols, which is the TCP and the IP protocol. So the TCP IP stack will be our main focus. But anyhow, we do it in order, bottom up. So let's talk about the data link layer first. So we know in the data link layer, framing happens. The challenge in framing is to detect from a bit stream the start and the end boundaries of a data packet. So if you go from the perspective of a receiver, where you get a bit stream, so a sequence of bits from the physical layer, you need to extract the frames in the correct way at the data link layer in order to make packets out of this bit stream. And the boundary detection is based on 2 things. There is a pattern, a distinct pattern, which is quite long. It's 8 bytes long, so 64 bits long, and we call this the preamble. So this is a pattern that distinguishes 2 frames. So this is basically the start boundary of a frame. So now you can ask a question, well, when we have a preamble, do we need an extra method to detect the end boundary? And the answer is yes. So the first thing is to get to the start of a packet from a bit stream, and then you need the information how long this packet is. Because these packets can be of different or variable length. You can have a packet that is 1,000 bytes, you can have a packet that is 500 bytes, you can have a packet that is 1,500 bytes. And although the likelihood is pretty low, close to 0, that the 8-byte preamble is part of the data that you want to transmit. We also call this the payload. The payload is the data that you actually want to transmit from one process to another. There's a chance, admittedly very low, that the bit pattern used as preamble is part of the payload. And if you do the end boundary detection based on the follow-up preamble, there is a probability greater than 0 that you miss a end boundary because the preamble is part of the payload. So in order to avoid that, you need to know the length of the packet. And the packet's length can be stored in the header, for example. And we will see that this is actually the case, but there's another story on the length field in the data link layer. So, but in theory, using the preamble and the length, we can detect start and end of packets and perform the packetting process on the data link layer, given the bits from the physical layer. For each layer, we introduce a study object, which is the most prominent protocol in the respective layer. And in the data link layer, this would be Ethernet 2, so starting from 1997. From time to time, the IEEE, which is the standardization gremium of Ethernet, publishes new versions of Ethernet, puts in new features, changes things, improves and optimizes things. But the gold standard of Ethernet is Ethernet 2, published in 1997. The most recent version of Ethernet was published in 2016, but I don't know the exact number. But 2016 was the last revision of Ethernet. So, but we focus on Ethernet 2. What you see in the diagram here, it's the Ethernet header. You read it from, you read it in like a bit interval, where on the left-hand side you have bit 0, for example, and on the right-hand side you have bit 1500 and something. And the header fields, the size of the header fields define where to find certain information. So let's start from left to right. Actually, not part of the Ethernet header is the preamble and the start frame delimiter, but I included it in the diagram such that you see how this preamble looks like. The preamble is a 7-byte field of alternating bits, so 101010, 7 bytes, so 56 bits long. And after 7 bytes of preamble, there's the start frame delimiter, which is a 1-byte field, which is always set to 10101011. If you combine these two, you get an 8-byte separator that technically do not belong to the Ethernet header. And these two, like the preamble and the start frame delimiter, are always in between two Ethernet frames. 8 bytes. It's almost alternating. It's alternating except for the last bit, because if it would be alternating, the last bit would be 0, but in fact it's 1. 8 bytes of alternating bits except for the last bit is set to 1. And this separates Ethernet frames in a bit stream. Next, there is MAC source and MAC destination. This is the concept or the way of physical addressing. It's a unique identifier. It's 48 bits long, and it's specific for the network card that you have built into your computer. So every network card ships with a pre-configured and pre-installed MAC address. And this MAC address, it looks like this. It is a 48-bit number, which we split into bytes, because 48 bits are 6 bytes. So each of these 6 groups that are mentioned on the slide are in fact the 6 bytes of the 48-bit number. And we represent 1 byte in a hexadecimal digit, and we separate them by colons. Sometimes you see also a dash as a separator sign, but typically these are colons. And this is how a MAC address looks like. Again, pre-configured, pre-installed in your network card. And if you plug in a cable and you connect 2 devices together, like 2 hosts or a switch and a host and such, the first thing that the 2 communication partners do if you plug in a cable into both ends of a connection, or of a like physical link, then the 2 devices, like a switch and a host, negotiate each other. And one part of the negotiation is an exchange of the MAC address. The switch decides based on the value of the MAC source and MAC destination, which port to put the input signal to. Because whenever you plug in a host into a switch, there's an initial negotiation where the switch learns the MAC address of the host that was plugged in. So switches know all the MAC addresses of the ports, and they can maintain this information in a table where MAC address like this one, 00005E and so on, is on port 1, and another MAC address is on port 2, and the third MAC address is on port 5. And when you send data to a switch, then you encapsulate the data into Ethernet frames. So we do packets, Ethernet frames. The actual data is part of the payload here. And you have the addressing information in the Ethernet header with the MAC source and the MAC destination. MAC source is the MAC address of the sender, and MAC destination is the MAC address of the receiver. And the switch takes a look at the MAC address of the destination, and this way decides on which output port to forward the signal to, or to forward the packet to. But in fact, it's an electrical signal. This MAC address has two parts. The first part is specific for the manufacturer. It's called the Organizationally Unique Identifier, abbreviated OUI. And this identifies the manufacturer. So the first three would be, highlight this, the first three would be these 3 bytes. These are for the manufacturer, and the actual network card, so the NIC, is identified by the last 3 bytes. We and you can check this out. So if you open a Linux console and type in the command IPA, for example, then you get a list of all Ethernet cards, physically and virtually. So I have a lot of Ethernet cards here because I do a lot of virtualization. But this entry, for example, in the list, this is my Ethernet. This is my Ethernet adapter. I guess this is one of the docking stations that I have. This is the second docking stations that I have. I have a docking station connected with an Ethernet port, and my network connection actually comes from the LAN cable that I plug into my docking station. So this is this interface here, and you see the orange entries here. This is a nice syntax highlighting, because the orange entries here, these are the MAC addresses, and I can do both. Let's see. Well, I know because I do it with other courses, but other courses, I do other courses in the lecture hall, and in the lecture hall, I use Wi-Fi connection. So I always do this exercise with my Wi-Fi Ethernet address. But now I'm at home and I plug in to my switch using an Ethernet cable. So I have an actual Ethernet link here. So I will try to find out what is the manufacturer of this Ethernet card that is built into my docking station. So I will copy paste my my MAC address here real quick, and then I browse to the standards OUI.IEEE.org. OUI.IEEE.org, and you see it here. So this is a very comprehensive list of all manufacturers of Ethernet cards, and my browser needs to take a while in order to process this very large document. But it's very large. And now, you don't see it. I have to move myself. So in the bottom left corner, you see that I'm searching for my my MAC address, but I do not want to search for my whole 6 bytes of my MAC address. I only want to search for the first 3 bytes. And you see the IEEE has not colons as separators of the bytes, but dashes. So let me change this up as well. And now we found our entry, which is Winstron Infocom Fushan. Never heard of this. So if we Google, it's an electronics company. Yes. Website doesn't open, or opens slowly. Yeah, it's a hardware manufacturer. So Wistron Infocom is the manufacturer of my network card that is built into my docking station. You can do the same exercise with your MAC address at home, and you get different results. Now let's talk about Ethertype. Oh, I said before, unfortunately, ether type is a thing. Let me go back here. Let me go back to this slide. Because ether type, it comes after the two MAC addresses. So the Ethernet header starts at here because preamble and start frame delimiter are between Ethernet frames. So what I marked here, this is the actual Ethernet frame. So it starts with MAC source and MAC destination. And then here in between, we have the ether type / length. And you can ask the question, can people not decide? Should it be ether type? Should it be length? And the question is, for a long time, people could not decide. So I will tell you the story about Ethernet. Ethernet was not invented by the IEEE. IEEE is the standardization gremium that standardized Ethernet, I guess, in 1984 or 1983, so early to mid 80s. And Ethernet was in existence by then. So who invented Ethernet? It's the company Xerox. Xerox is a company that manufactures printers, scanners, basically the towers that you see in offices. And they have a business interest for printers and scanners and computers talking to each other. So they did a lot of research in that regard, and they invented Ethernet in 1998. Now, 1980, in 1980, the beginning of the 80s. And they manufactured devices, they manufactured Ethernet cards, they developed the protocol, they basically did everything. And the IEEE decided, well, let's standardize this, which is good. Industrial standards are good, and the IEEE does very good work. But the IEEE did changes in the Ethernet frames that were initially developed by the Xerox company and changed the purpose of a field. And the field that I'm talking about is the field in red here. It's ether type length. Xerox said, we need to use the field as ether type. Ether type is a field that indicates which protocol is encapsulated in the payload. So at the data link layer, you need to know if you process packets in the operating system. So the data link layer happens in the network card driver in the operating system. So this is in kernel space. This is a device driver where the implementation of the data link layer resides. This is part of an operating system. And after the data link layer is done with all the jobs, like when error correction is, or error detection is done, when flow control is performed, when all the addressing stuff is done, then the Ethernet frame needs to be passed to the next layer, right? To the network layer. But we have multiple implementations for the network layer. We have IPv4, we have IPv6, we have ICMP, we have ARP. So how can the data link layer know to which protocol in the network layer to forward the packet to? That is a trivial but sincere question. So the people, the engineers at Xerox decided, well, we need to pack that information into the data link layer. So the data link layer needs to know what is the follow-up protocol. And this is the ether type. It defines, the value is basically a number, right? It's, I guess IPv4 is 8,000 in hex. So it's a number that you put in the ether type field. And based on the number, the operating system can decide that the Ethernet frames are passed to the IPv4 implementation. So this field is important, but IEEE, in the course of standardization, decided that this is a layer violation. We have the ISO OC7 layer model, and these layers, that's the idea of layering. I can understand the argument here. Yeah, the idea of layering is that the layers can operate independent of each other. And having the information from one layer to another layer would be a violation of this separation and independence. So IEEE change the ether type field to the length field in the standardization process. And people were not happy because the product was on the market for 4 years already. So customers were not happy that they have devices that do not follow the standard. Xerox was not happy because they invented and developed Ethernet, and they need this field. They produce the hardware. The hardware manufacturers were not happy. Software manufacturers were not happy. Customers were not happy. Manufacturers were not happy. The whole world, except for IEEE, was not happy. So there was a dispute that went a long time. In fact, from 1984 to 1997, because then the IEEE, they gave up, they conceded, they decided that, okay, let's do a compromise. Let's say that values below 1500 are interpreted as the length of the packet, and values bigger than 1500 should be interpreted as ether type. This change was introduced in the standard in 1997. Why does that work? Because the Ethernet payload, like the physical layer, cannot handle packets bigger than 1500 bytes. So the maximum size of an Ethernet frame is 1500 bytes in the standards. I know there are jumbo frames that came later and so on and so forth, but the gold standard is the payload of an Ethernet frame is 1500 bytes at max, at least 46. So it ranges from 46 to 1500 bytes. And if here in these 2 bytes before is a value lower than 1500 bytes, well, then we interpret this as length. If a value of bigger than 1500 bytes, well, if the value of these 2 bytes in between MAC destination and payload, if these are bigger than 1500, then it cannot be a length because the length has an upper limit of 1500 bytes, and therefore we interpreted it as ether type. What happens in practice? In practice, we use ether type all the time because the length, I said it before, the length is an important configuration parameter because the preamble and the start frame delimiter are not enough in order to find the start and the end of an Ethernet frame. But the length, well, but the packets of one flow, so if you transfer a file and you have 2 million packets, these 2 million packets that belong to the same like traffic flow of data, they always have the same length. It does not happen that one packet of the same flow has a different size as another packet. So what you can do, and what people did, this is implemented in practice, is that the length is predefined in the operating system. So for all Ethernet frames that you handle in your network card, you say all packets have the same size. And if all packets have the same size, you don't need the information of the length of a specific packet here in the Ethernet header. So you can, in fact, use the ether type for the 2 bytes here between destination and payload. You can also see this in the terminal. So again, here is my Ethernet interface, and here is my Wi-Fi interface. So I have one. This is the MAC address of my Wi-Fi interface. This would be the IP address of my Ethernet interface. This would be the IP address of my Wi-Fi interface. But there's also an important value here, MTU 1500. It's the maximum transfer unit, and it's set to a value of 1500. And here on my on my Wi-Fi interface as well, basically on any interface, because it's the standard. It's the default value. The maximum transmission unit, is it transmission unit or transfer unit? Doesn't matter. Maximum transmission unit, 1500 bytes. These 1500 bytes comes from the upper limit of the Ethernet standard, allowing a payload of up to 1500 bytes in an Ethernet frame. Okay. So we've talked about the preamble. We talked about the start frame delimiter. We know that physical addressing is based on MAC addresses. I told you the story of the ether type field and the dispute with the IEEE. Then the payload comes. Payload is like the data that you want to transmit. And then the CRC. We do not talk about the CRC in depth because we simply do not have time. So we skip the CRC, which is lucky for you because students experience the CRC as a difficult concept where in fact it is not. But anyhow, the CRC is a error correction code. It's called, or it's abbreviated from cyclic redundancy code. Look it up. Cyclic redundancy checks. So CRC is cyclic redundancy checks, which is an error detection code, which is based on some math. What you do in CRC is polynomial division, and you're interested in the remainder of the polynomial division. So you interpret a k-bit frame as a polynomial with k terms, and then you do polynomial division onto it. And if the remainder is a certain value, then it's fine. And if the remainder, the certain value is 0, by the way. So if the remainder of a polynomial division that you do at the receiver's end, and if you get a remainder that is not equal 0 at the receiver's end when you do this polynomial division again, then this is a strong indicator that the packet is compromised, and you should treat it as a compromised packet. So there was a bit flip or multiple bit flips in there. But if the remainder is 0, so this is a checksum calculation, if the remainder is 0, then you should be confident that the packet was delivered successfully and uncompromised. And we will skip the method. It's also excluded from the exam, and we do not do the cyclic redundancy check. So you are relieved of polynomial division in this course. A word regarding feedback-based flow control. This is the approach at the data link layer defined in the Ethernet 2 standard, how flow control can happen, like regulating the pace at which the sender sends to the receiver. Feedback-based means that the sender by itself does not detect if the sender is overwhelming a receiver. It's based on feedback. So the approach here is that the feedback, that the receiver gets back to the sender with the feedback that the receiver is currently overwhelmed. And this is an Ethernet frame, a special Ethernet frame, which has a value of 8808 hex in the ether type field. This is called a pause frame. And this frame is special because if the sender receives such a frame with ether type 8808, then the sender pauses transmission. For how long? This is defined in the payload. The payload carries an opcode, it's like a control code, and in the opcode, there is the information how long the sender should pause transmission. So ideally, when the receiver has the resources in order to handle the data volume from the sender again. Unfortunately, fortunately, there are better methods than feedback-based control, because feedback-based control is binary. Either the sender sends at full speed or the sender does not send because it received the pause frame. And this like binary decision, sending at full speed or not sending at all, these has inflexibilities. And it contradicts to the fairness goal that we have. Because if 5 senders are sending to a receiver, and the receiver decides to like silence or pause 2 of the 5 senders that are currently sending for half an hour, then this is not fair. It depends on more or less luck, which sender the receiver selects in order to be paused, in order to reduce the volume of the data that comes into a receiver. So this violates fairness. And also what we want is network convergence, in the sense that, well, if 5 senders send to one receiver, receiver is overwhelmed, then the senders should detect automatically that they are overwhelming the receiver and reduce the data rate at which they are sending accordingly, such that the 5 senders detect, ooh, the receiver is not good, I reduce my data rate by half, for example. And this is a better way. And this kind of flow control cannot happen at the data link layer, because the data link layer does not have the tool sets in terms of the rules in the protocol in order to sophisticated flow control. So we have basic flow control in the data link layer with feedback-based flow control and pause frames. But when we're talking about the transport layer, the TCP protocol, the TCP protocol has a way more sophisticated way how to deal with flow control and not overwhelming a receiver. So we are leaving the data link layer and proceed with the network layer. Does anyone have a question so far? Okay, then we proceed. Transitioning to the network layer. The network layer has the following tasks to be done. Routing. Routing means calculating a path or a packet. So routing is done specifically for a single packet from the source host to the destination host in context of the global network. So in context of the whole topology of the network. Routing is easy on small networks. Routing is complex at big networks. If we take the internet as our prime example, then routing is in fact a challenging task, because it's an end-to-end task. Because the source host and the destination host typically do not lie in between the same subnet. So you remember the structure of scaling networks up is to construct a hierarchy of networks, such that we have networks of networks. But routing is done on a global scope. So it's a challenge of end-to-end transmission. And we saw in the example before, I can show it again. So let me log into my home server real quick and do a trace route to the Technical University of Munich. There you see that I'm traveling through at least, let's say, 9 subnets, not counting in the first one, from my home network that is in a small town in the Bavarian forest to the capital of the state of Bavaria, which is Munich. And the packets travel through around 8 to 10 subnets. So these packets need to be routed. So how do the packets find the way from source, my laptop, to destination, the web server of the Technical University of Munich? So the challenges in routing are learning the topology of the network, because my laptop does not know the topology of the internet. And the topology of the internet, we talked about it before, it's chaotic, it's huge, it's unwieldy, and it's complex. And routing means that we need to coordinate this traffic across multiple subnets. We need to take care when coordinating the traffic. It's the same as you drive on the road and use like the street network of a country. You have construction sites, you have traffic lights, you have traffic jams, and the same challenges apply for network packet transmitted in a network. So you need to carefully choose the traffic flow to avoid overloading network control devices, so do flow control properly. You should avoid traffic jams. The technical terms for traffic jams in networks is called network congestion. So you should avoid congestion, and you need to calculate detours in for links that are offline, or wires that are broke, or routers that are broke. So these are the typical challenge of an end-to-end transmission, and it all boils down to finding an optimal route from source to destination. You can obtain these routes in two ways. The first way is you do it manually. So you have network engineers that know like parts of the topology, that know or have a deep knowledge on networks, and they can create these routes for packets manually. The second approach is you can have algorithms to do so. Both have benefits and drawbacks. Doing it manually, then you have a hand manufactured and a hand configured network where you can calculate in information that cannot be processed by an algorithm, for example, like time aspects. And network engineers can use their know-how to make really good and close to optimal routes in a network. So the quality of the routes can be good or can be better when we do it manually. But I mean, algorithms are also quite good, and algorithms are good in rerouting. So algorithms can detect if a route is not available anymore and can calculate a detour like a navigation system in your car. Unfortunately, we do not have time for routing algorithms. So we focus on routes that are established and set by network engineers manually. So we assume that the routes that the routes are already defined. And what we focus on is what a router does with these routes. Because routing is based on a routing table. It's a table that stores the way from source to destination, one part of it, one hop, in a table. So basically the routing table identifies the follow-up subnet for one packet. And an entry in the routing table is called a route. And these routes are typically defined by network engineers. And this is a crucial information. The routing works not basically not routing algorithms, because routing algorithms create routes, but the algorithms that perform the routing, that actually do the forwarding part. These are done on basis of a single packet. So the end-to-end transmission, the challenge is tackled not by a single device, by a single entity, but for each subnet individually. So whenever a packet arrives at a router identifies the next subnet to forward the packet to, and then call it a day. The one router only defines the next hop. And if the route is good in any sense, then the route should bring the packet one step closer to the final destination. But then, eventually, the packet arrives at the next router of the next subnet. And then the next router does the same thing. So routers only make a routing decision only based on their proximity. And also, they do the decision just for one step and forward like the routing problem to the next router. Then this next step should bring, as said, the packet to the one step forward to the final destination. But this is how routing works. It's always single stepping. Let's do a minimal example. So consider this very small network. Well, it's a network that consists of 3 subnetworks and has 4 routers in it. So the clouds that you see here, these are subnets. And the boxes here, the red boxes, these are routers. We have 3 subnets, A, B, C, and we have routers 1, 2, 3, 4. Topology is as follows. In terms of topologies, we do not know anything about the topology inside a subnet, so this information is not given. And a connection of a subnet to a router, like this one here. This means that this router is part of the subnet. So this is the syntax of this diagram. So R4 is part of C, and also R3 is part of the subnet C. So R3 and R4 are in fact in the same subnet, subnet C. And the same applies for R2 and R3 for subnet B. So R3 is in subnet B and in subnet C. And R3 and R2 are in a subnet, which is subnet B. And this is how routing basically works. You need to chain together the subnets and the links where the packets travel. So if a packet arrives at router 4, for example, and it needs to go to router B, then because router 4 is not directly connected to the subnet B, the router 4 needs to forward the packet to a next hop, and then let's see what the next hop does. So the next hop for the packet, the blue packet, will be then traveling through subnet C, and as router 4 and router 3 are in the same subnet, you can directly talk to router 3. So they are basically connected together with a switch. And router 3 is also connected to subnet B, and as the destination, let's say subnet B. And the rules to which device to forward to is defined in the routing table. You see the routing tables of the 4 routers on the slide here. So for example, if a packet arrives at router 4 and the packet is addressed to subnet A, so the destination is A, then our next hop would be router 2. Because router 2, router 4 are in the same subnet C, so they have a connection. So the packet is forwarded from 4 to 2. If we take a look at 2, destination is A. A does not have a next hop because A is directly connected to router 2, so router 2 can forward the packet to its final destination. I'm doing it again. So a packet arrives at 4. So the routing table of 4 is considered. And the routing table, you see it here. The routing table maps subnets to routers. So if the destination is A, then you forward it to router 2. And you can do this because router 2 is part of the subnet C. Now the packet is at router 2. The router 2 takes a look at the routing table and sees destination is A. Yeah, well, A is directly connected to me. There is no next hop. So the router will then just directly deliver the packet, like sending it to the switch of the subnet, and then the switch is taking care of the packet. And forwarding it to a host H. So this is how routing works. How can a protocol realize routing? For that, let us introduce the IP protocol. Before we talk about the IP protocol, we need to clarify a concept, which is called fragmentation. We talked about the MTU before, the maximum transmission unit. This is the largest size of a network layer protocol unit, like an IP packet or a packet in the network layer, that can be transmitted in one packet of the data link layer. And as we know that the data link layer's upper limit in the payload is 1500, the default value of the MTU is also 1500. It's the size of the packet in the data layer. Period. The size of the packet in the data layer. And it's also a configuration parameter in the network layer. Well, you can make this bigger or smaller. And the question is, are smaller packets better than bigger packets? And this is a trade-off. If you have large MTU values, then you have bigger packets. The amount of payload increases. And this also minimizes the overhead. There's an overhead that's introduced by all the headers. So if you have a big header and a small payload, then you have a large overhead. So if the ratio between payload and header size is out of balance, then this is bad, because then you mostly just transfer headers instead of the actual payload. So you want to transfer the payload, right? This is what the user is interested in. And if you have a lot of header information in there, then this reduces the performance. So the smaller the MTU values, the smaller the packets, the less the efficiency, but also the lesser the delays. If you have a smaller packet, you can transfer the packet faster through the network. So if you have a packet that's a kilobyte of size, that goes through the network faster than a packet that has a terabyte size. So you need you need more time to transfer a terabyte over the network. If we make it too large, then we reduce the amount of, or we reduce the ratio between header and payload, which is a good thing. But also then we have big packets, and big packets are more likely to be corrupt. So the likelihood of a 10 megabyte packet to get corrupt is 10 times higher than the likelihood of a 1 megabyte packet to get corrupt. So the higher MTU values, the higher the risk of corruption. So what you do in practice is you go to the maximum. Maximum in Ethernet is 1500 bytes. It's not too large. The actual frame size is 1518 bytes because 1500 is the payload. And 18 bytes, if we go back, see this. So 18 bytes is the header. 6 plus 6 is 12, plus 4 is 14, 4 bytes CRC is 18. So you have 18 bytes in the header, not counting in preamble and start frame delimiter. Upper limit on the payload is 1500 bytes. If you add these two numbers together, you get to the Ethernet frame size of 1518 bytes. For network layer packets, this means that you should yield to an MTU of 1500 bytes. Because then if your network layer packet is 1500 byte, it fits into an Ethernet frame. Why I'm telling you this? Because the network layer, or to be more precise, the network protocol IP has a feature that's called fragmentation. So fragmentation is, well, is dividing larger packets into smaller ones. Basically, you put a hammer onto the packet and you split a large packet into smaller fragments, into smaller like pieces, as you see it in the diagram here. And here, so this is it. In the network layer, you can build packets of a bigger size. So you can have a 2000 byte packet. But 2000 is bigger than the MTU because the MTU is 1500. The MTU is the largest size that can be transmitted in a single data link layer transaction. And the max value, or the maximum size of a data link packet of an Ethernet frame is 1500. So for IP, the value of the MTU is 1500 by default. But if you, for any reason, say you want IP packets that are of 2 kilobytes of size or of 8 kilobytes of size, then you need to split them up. Then you split the large packet that you have here on the top into pieces, smaller packets. And here you see the drawback clearly. If you split one packet into 3, then you have 3 times the header, right? And the ratio between header and payload gets worse. But then the fragments here are smaller than the MTU, and then they can be transferred using an Ethernet frame. Fragmentation in general should be avoided and is bad. It's poison for network performance because it introduces another step of like packetization. We have already packets, and there is no good reason for people not sizing these packets optimally or properly. So if you decide for your network layer implementation to have large packets that need to be fragmented in order to fit to the data link layer, then you are not a good network engineer, because then you introduce the second packetization step. And there is no good argument for having fragmentation at the network layer. Okay, anyhow, with that knowledge, we take a look at our study object, which is the Internet Protocol. Internet Protocol, introduced by the famous paper of Cerf and Khan, 1974. The paper is linked in the slide here below. And this was groundbreaking work. There are a lot of information in this, I don't know, 10 pages paper. We have the notion of network scalability with the idea of building bigger networks out of smaller networks. So the subnet idea comes from this paper. And then the IP protocol was sketched in the paper, and the TCP protocol was sketched in the paper. So basically one single paper, one single work of 2 people invented networking, invented how we exchange information, and in consequence also invented the internet. They have been awarded with the Turing Award in 2004 for their groundbreaking work, because in the early 2000s, mid-2000s, the internet really took off. So before, the internet was like, okay, we have it, it's nice, but it's expensive. But in the mid-2004s, people started to use the internet extensively. Turing Award, by the way, equivalent to the Nobel Prize in computer science. So there is no Nobel Prize for computer science. There's only a Nobel Prize for chemistry, for peace, for physics, obviously. That's it. Mathematicians have the Fields Medal, and computer scientists have the Turing Award. Okay, IP, the IP protocol. There were lab versions, version 1 to 3. They were experimental, developed in the 70s, never saw the light of public. The first version of the IP protocol that was published is IPv4. Oh, when was it published? Somewhere in the 80s or late 70s. But IPv4 is still, in 2023, almost 2024, the dominant protocol in use. We still have IPv4. We have IPv6. In between is IPv5 that no one uses. So IPv5 was also published and standardized with an internet stream protocol. No one uses IPv5. And from 2006 onward, we have IPv6. And IPv6 addressed a important issue, which we will talk about in a bit. At first, let's focus on IPv4. Here we have the header of an IPv4 packet. An IPv4 packet is called an IPv4 datagram. And this is the structure of the header. And I will explain the header from bottom to top. Because the bottom is easy. Well, maybe a word or two about how to read the header. So the header is a sequence of bits that carries like metadata about a packet, like the total length of the payload or some addresses and such. And reading Ethernet header is easy because the Ethernet header, it's just 18 bytes, right? There we have it. So the first byte is here, last byte of the frame is there. So it fits into one column. This header of the IP protocol has a lot of information in it. It does not fit into one column. So I decided to illustrate it in 32-bit rows. So this one here, this is bit 0, right? It's the first bit of an IPv4 datagram is bit 0 because we as computer scientists, we start counting at 0. Meaning we have bit 31 here if we start counting at 0. That means that this bit here, the first bit of the second row is bit 32, and the last bit of 32 is 63, because the first bit of the third row is 64, and so on and so forth. So this is how you read the header. In practice, it's a bit stream, but to illustrate it properly, I decided to go for rows of 32 bits length. Now let's discuss the fields that are in the header. We have options. So the first information of an IPv4 datagram is that the header is variable in length because the options are optional. You can have some extra space for custom defined options that you want to put in an IPv4 datagram. In reality, no one uses the feature. In practice, options are always missing. But for completeness, options would go here. Then, traveling from bottom to top, we have the source address and the destination address. And these are the IP addresses. The IP address of the sender in the source address and the IP address of the receiver in the destination address. And one important fact is that source and destination address, the field has a length of 32 bits. Keep that in mind. 32-bit addresses. Unfortunately, I do not have something to drink here, and the break is imminent. Let's try to finish the header, then we go to the break. So source and destination address, IP addresses of sender and receiver. Then we have the third row here. The header checksum also checksum value. It's a checksum value. Excuse me. Yeah, let's do a break. I have to drink something. Let's do a break and then pick up on the IPv4 header again. 15 minutes. Talk to you soon. So welcome back, everyone, after the break. Hopefully I recovered my voice because I have coffee now, which is good. And also to be more prepared, but it's still super hot. I'm doing double cup now. So let's pick up on the IPv4 header. So options variable, source destination addresses. These are the IP addresses. The important aspect, 32 bits in length. And then we have the row here, time to live protocol checksum. So checksum is the same as CRC. It's an error detection code where you can detect based on a mathematical calculation if the packet was compromised, yes or no. Compromise meaning that a bit flip occurred or multiple bit flips occurred. Then protocol. Protocol is the field that is equivalent to the ether type field in the Ethernet protocol. So in the protocol field, the next following up protocol is defined. So this is a value that specifies what happens in the transport layer. Are we using TCP? Are we using UDP? Are we using QUIC in the transport layer, defined by protocol? Then we have time to live. Time to live, unfortunately, is named wrong. Because what this time to live field does is it constitutes an upper limit of the number of hops a packet is allowed to travel. And this is required and important because networks or network engineers can make mistakes. Also, algorithms can make mistakes. And there might be, in context of routing, there might be a circle in a route. And this happens. This happens all the time. This happens on a day-to-day basis. So if we consider a network that is as large as the internet, one does not know all parts of this network. It's impossible to know. So from time to time, it happens that some subnets are configured in a way that they are routed in a circle. For example, let's go one back. So if R4 routes to R2, R2 routes to R3, R3 routes to R4, then you have a cycle. Packets that are in these cycles are there for all eternity because they're going round and round and round and round and round through this cycle. So what are you doing in this case? You define the maximum amount of hops, like a hop being traveling from one router to another. And we define an upper limit for that. This is time to live. And every router that processes a packet decreases this value by 1. So if you start at a value of 50, the first router decreases the value to 49, the next router to 48, the next router to 47, and so on and so forth. So you have an upper limit in the amount of hops packet can do. And if this limit reaches 0, the router then just drops and discards the packet. Period. Okay. The second row here, this is purely for fragmentation. This is the reason why we talked about fragmentation. We have a couple of fields here. We have fragment offset and we have identification. In case of fragmentation, so if someone decides, as opposed to every recommendation out there, to enable fragmentation, then you do the fragmentation, but also you need to reassemble the fragments to the message again. And for that, you need 2 informations. Let's say this this packet that is fragmented is packet, and we say this is packet A, right? then the fragments also needs the information from which packet the fragment was split off. So you store the information that this is packet A in each of the fragments. But in addition, you need the information of the ordering. So you need the information that this packet is fragment A1, this is fragment A2, this is fragment A3. So you need to identify the fragments to which of the fragments belong together, and you need a concept of ordering in the fragments. And exactly these two tasks are the fragment offset. So this would be 1, 2, 3, and so on. And identification. This is like A. So all the fragments that belong together have the same value for identification. And fragment offset defines the order in which we need to reassemble the fragments in order to get the whole, the big packet again. These flags, there are 3 flags in there. A flag is a single bit value. A flag is like a control element that you can toggle on when it has a value of 1, or you can toggle it off if it has a value of 0. There are 3 flags in there, but only one flag is important. It's the DF flag. DF is don't fragment. Don't fragment. Horrible writing with a mouse. Fragment. And if this flag is set to 1 and a router sees a packet that is too big, because a router can have a MTU value that is smaller of the size of the packet the router is supposed to process. If the don't fragment is on, then the router drops the packet. It does not process it because fragmentation is disabled. Don't fragment means we are not allowed to perform fragmentation. If the don't fragment flag is off, so there is a value of 0 in there, then routers are allowed to fragment. And if they encounter an IP packet that is too big for their network card, then they perform the fragmentation process. If a router drops a packet because of don't fragment, typically the router gets a feedback message back to the sender saying, well, I have received a packet of you that's too big for my network card. Please reduce it in size. This is why this is important. And last but not least, the last row is version. There's a value of 4 or 6 in it, if it's an IPv4 or an IPv6 packet. IHL is internet header length. Internet header length means that we need the field internet header length because the header is variable. Right? We have a variable field here, which is options. Options can be there, but they doesn't have to. In order to split the header from the actual payload, you need to know how long this header is if it's variable. If it's fixed, then you know it, because then it's a fixed size. But if the header is variable, you need to know how long this header is. And the length of the header is IHL. The total length then, the total length of the package is then in total length. And then we have, last but not least, a field that's called differentiated services. Differentiated services is also a field that is named wrong, because what this field does is it introduces the concept of priority. You can assign a priority to an IPv4 packet. Does it have a high priority or low priority or standard priority? And this way you can like skip the line skip router queues, and routers will then respect this priority and process these packets according to their priority levels. So differentiated services, the values in this field are numbers that define a priority value. Use cases are typically voice over IP and web browsing. So my box from the internet service provider, I have a Fritz box, which is typical in Germany here. And the IP packets that are created when I'm doing a phone call, so when I'm using voice over IP, these packets have a higher priority than packets that are created by any other device on the network, like my laptop that is doing web browsing. So when it comes to bandwidth problems, so I don't know, my wife is watching 5 Netflix streams at the same time, then I have a guarantee that my traffic from my phone is prioritized over the 5 Netflix streams from my wife. We can do this with differentiated services. Okay. The next slides are just descriptions what we talked about before. So for the exam preparation, you have the description of all these flags here as well. What we do next is, well, at first, I want to clarify. Yeah, well, no, let's do the task first. So let's switch over to my browser. Let's do a task that's called IPv6. Here it is. So we have seen the IPv4 header, and this is the IPv6 header that you see on the browser here. And just by looking at the IPv6 header, here you have, I'm going back to the IPv4 header. So here we have IPv4, IPv6, IPv4, IPv6, IPv4, IPv6. So just at looking at the structure of an IPv6 header, you can realize that the IPv6 header is less complicated than the IPv4 header. This was one of the design goals of IPv6. Reduce the number of fields and throw out fields that we actually do not use in practice. Make things simpler, because this is an engineering principle. If we can have a simpler solution for the same task at hand, the simpler solution has more value than the complex solution. So this is the IPv6 header, and what I want you to do is to do research and compare the IPv4 header with the IPv6 header and name the fields that were added, changed, or removed compared to IPv4. For each changed or added field, please describe the purpose. So when a field was introduced more, you should be able to describe what is the purpose of that field. Or if a field has changed, why has it been changed? And is there any difference in purpose? This is the first part. And the second part, please do it as well. This is the bit interval. So by taking a look at this header, at which bit interval is the next header field located? And please use the interval notation, which is defined here from bit I to bit J, where we start at index 0, starting counting at 0, and this is the interval notation. For that, you have, how long do you have? You need to compare, you need to discuss, let's say 15 minutes for the comparison and 5 minutes for the bit interval. I will do breakout rooms again, so you can discuss in your group and hopefully come to a conclusion. Before I start making breakout rooms, does anyone have a question? No? Okay. Then I'm creating the rooms and opening the rooms now, and we discuss the task in 20 minutes again. You can join your room now. at the difference between IPv6 and IPv4. And I do this by taking a look at the more complex header, which is the IPv4 header, and strike out what was removed in the IPv6 header. So you compare it with what you came up in your group. The first thing that is quite good is that options were removed. No one uses it. And in IPv6, we want to make things a little bit easier. And if we have a field that is not used, but introduces other challenges, because the option field in the IPv4 header makes the header variable. And if the header is not variable anymore, you don't need the length of the header. So the IHL, the internet header length, is also removed from the IPv6 header because we don't have any options anymore. And as we have no options, the header is not variable anymore. If we have no variable header, then we don't need the length. So this was removed. Next, header checksum also removed. Perfect, because we do checksumming at the data link layer already. So we don't need to do it at the network layer again. Next, what was striked out, and this is very good, the whole fragmentation feature was removed. So identification, fragment, offset, and flags were removed because no one uses fragmentation. You should not use fragmentation. If you need fragmentation, you configure your network wrong. So instead of using fragmentation and get more poison into your network, please fix the network configuration. Okay, then next, what has changed? I do changes. Oh, well, the field that stayed the same, I do it. The only field that stayed the same is this one, version. I will underline it. Version stays the same. Total length was renamed to payload length. Look, total length is different from payload length because total length is the sum of the header length plus the payload length. And payload length in the IPv4 header, we have it here, just has the payload length because we know that the IPv6 header is 40 bytes in total, period. It's not variable, we know it, it's static 40 bytes. Okay, so total length was repurposed and renamed, but well, it's a length parameter. Then protocol was renamed to next header because it's a more appropriate name. Time to live was renamed to hop limit, I guess. Yes. So next header is the old payload. Then we have hop limit. Hop limit is the old time to live. And then finally we have the differentiated services, which were renamed to traffic class. The same purpose, it's for prioritizing packets. Traffic class, a way clearer name for having a priority based on traffic classes that you define in these bits. And then the elephant in the room. What has changed also is source address and destination address. Because source and destination are 32 bits in the IPv4 datagram. In the IPv6, we have not 32 bits, but I hope you can see this. These are 4 rows. So in total, 4 times 32 bits, which is 128 bits. Why is this important? Because with 128 bits, we can have larger numbers. We can represent larger numbers with 128 bits rather than 32 bits. Let me illustrate this real quick. Does this work? Yes, this works. So if you count in binary, let's say we have the following values. Let me move this a little bit to the bottom here, where we have the binary value here and the decimal value there. And you need to take a look at the number of digits, because the number of digits is the number of bits we require in order to represent a number. So for numbers 0 to 4 to 3 including, so for the first 4 numbers starting at 0, 0, 1, 2, 3, we need 2 bits. The decimal number 4 is the binary number 100. So we need 3 digits in binary for representing the decimal number 4. And then we have 5, 6, and 7. This is 101, 110, 111. And next, we have 8. 8 is 1000 again. It fit on one? Yes, it does fit on one screen. So the higher the number is, the more digits we need in binary to represent the number. The first 4 we can represent in 2 bits. We need 3 bits in order to represent a number up to 7. And we need 4 bits from 8 to 16. And there's a pattern in there. So this is the number. Let's say we have n bits. For n bit, for n bits, we can represent numbers up to 2 to the power of n minus 1. This minus 1 is because we start from 0. What that means is, if we have 4 bits, for example, so n equals 4 means that we're 2 to the power of 4 minus 1, which is the range of the numbers we can express from 0 to, what is 2 to the power of 4? Well, it's 2 times 2 is 4, times 2 is 8, times 2 is 16, minus 1 is 50. So in order to represent numbers in between 0 and 15, we need 4 bits in binary to represent it. Now, what if n is equal to 32? Let me clear this up, because you see, it's 1 row and we have 32-bit addresses. Starting from 0, this means that we can express numbers 2 to the power of 32 minus 1. And this is around 4 billion. So we can express 4 billion numbers with 32 bits. And in the mid-70s, people thought, well, 4 billion addresses. So with 32 bits, we can represent 4 billion addresses in total. Sufficient, right? But nowadays, we live in the time of the internet. And in fact, the whole address room, so every IP address, every number, every binary number that you can express with 32 bits. It's allocated in the internet. We do not have any IP addresses left in the internet. There's a black market for IP addresses. So if you own like a couple of thousand IP addresses, you can trade them, you can use them, you can trade them, you can make a fortune out of them. But all 4 billion IP addresses are reserved now. The organization that gives out IP addresses, at least in Europe, is RIPE, Network Coordination Center. It's like the European center where you can get IP addresses. Well, not anymore because every IP address is gone now. But like 10, 20 years before, if you as a company or as an organization needed some public IP addresses for the internet, you went to the RIPE organization, which manages the IP addresses of the internet, at least in Europe. Yeah, let's calculate 2 to the power of 32. It's 4,294,967,296 IP addresses that you can obtain there. And this is, again, this is the major weakness. And if we go back to IPv6, IPv6 tackles the address shortage in terms of increasing the number of bits that you can use for source and destination address to 128. 2 to the power of 128 is a lot. It's really a lot. Can we actually see what this number is? Yes. So it's 340 undecillion. I did not know before what an undecillion is, but these are 340 billion. It's a number that has 39 decimal digits. It's a very large number. It's this number here. So hopefully, in the near future, this 128 bits for the IP addresses will last a little bit longer than 32. So by comparison, we have 39 decimal digits and 2 to the power of 32. We have barely 10 decimal digits. Look at this small number here compared to 128. So this is the main reason why IPv6 is necessary. So we know IPv6 is necessary, but the thing is, IPv4 is still dominant because, yeah, the internet moves slow. So new technology, because it's such a huge thing and so many players are on the field when it comes to the internet, changing a protocol, a core protocol, such as the IP protocol, to a newer version, it takes decades. We are in the middle of the transition from IPv4 to IPv6. But this, sometimes it gets a little faster. Then some big company decides, well, we do not allow email sending on IPv6, Google, and so on. So sometimes you make a step forward, sometimes you make a step backward. But still, in 2006, IPv6 was standardized, published, ready to be deployed. But we almost have 2024, so almost 18 years later, well, IPv4 is still dominant. If you ask yourself the question, well, can we just force it and say, well, we'll pick a date and time and say on the 1st January of 2015, the whole internet switches to IPv6. You cannot do this because there is no global steering committee, which is a good thing because decentralized is not always a bad thing. and it will break the internet. And this is, it so much depends on the internet, so much businesses, the welfare of people depends on the internet of being operational. So you cannot just simply say we switch to a new technology and everything will be good. Then you end up in a situation, let me Google that meme. Everything is fine. Everything is fine. So you end up here. Everything is fine. So I guess we need to wait a couple of more years / decades in order for IPv6 to become dominant. Does anyone have a question? Okay. Now let's talk about IP addresses. So far, we know an IP address is a 32-bit binary number. It's in the source and destination address fields. And an IP address is global in the network. So two hosts on the network are identified by two distinct IP addresses. Routers in between. I mean, what a router actually is a router is a device that has a lot of network cards built in, but it's basically a computer where you have a couple of network cards, and every port in a router refers to a network card. So a router has several IP addresses, one for each port. It's clear because routers are in different subnets. So routers connect subnets together. And if an 8-port router is connected to 8 other routers, then this router connects or interconnects 8 different subnets with each other. And the router has an IP address in each of the connected subnets. A host can have multiple IP addresses as well. Whenever you have, or if you have multiple network cards, you can build a computer with a lot of network cards in it. You can have an IP address of a different subnet on your network card, assigned to a network card. You can even have multiple IP addresses on the same network card, but then the IP addresses need to be in the same subnet, the technical limitation. We did IPv6 already. Let's see how IP addresses look like, because they are written up in a special form, which is called the dotted decimal notation. So here in the slide, you see the binary form, 32 bits long, just a binary number. But we write this big number up in 4 octets, so in 4 bytes, the same as for MAC addresses. So we separate the bytes in a MAC address. We do this with an IP address in the same way, but we separate the bytes with a dot instead of a dash or a semicolon. And this is called the dotted decimal notation, because you take the first byte, the first 8-bit, represent this as decimal number, and then just write a dot to say, well, this is the first byte. The second byte here is the next 8 bits as decimal number, dot. The third byte as decimal number, and so on and so forth. So this 32-bit binary number is written up in 4 octets, like 4 bytes, that are represented as their decimal value. And this is an IP address. I assume that some of you already saw these IP addresses. And with an IP address, you can identify a network card. A network card is built into a host. So transitively, a IP address identifies a host. It's the same as your address at a house. So if you have an apartment or you have a house, this house has an address. It's the same concept for IP addresses and hosts on a network on a global scale. So an IP address is an identification for a host, or to be technically correct, for a network card that is built into a host. Now we come to a part where a couple of you do not know that an IP address carries two values. An IP address is composed of a network portion and a host portion. The network portion identifies the subnet the host is in, and the host portion identifies, well, which actual host within the subnet is addressed. So the addressing mechanism is twofold. The network portion identifies the subnet, and the host portion identifies the host inside that subnet. You cannot see by just looking at this 32 bits, what is the network portion and what is the host portion. The network portion is of variable length. Sometimes it's 8, sometimes it's 24 bits, but it's measured in bits. It's the top n bits are the network portion, and the remaining bits, 32, because this is 32 is the total length, minus the network portion equals the host portion. And this brings us to the term of a subnet. So again, the whole networking idea is to compose a larger network by combining or spanning a large network and decompose a large network into smaller subnets. And we do this on different levels. So the internet would be the largest network, and then we decompose the internet into this subnet, and that subnet. And these subnets are further segmented into further subnets. So a subnet is a segment of a larger network. And this segment is characterized by a specific range of IP addresses. And we do that because we can manage smaller subnets easier than bigger subnets. So we do this for organizational, routing, and security reasons. Routing reasons, because the smaller the networks are, the fine-grained the paths get, and the more optimal we can do routing. Organizational, obviously,